It is a pleasure to welcome you to the third edition of the lecture series on advancements in geotechnical engineering, from research to practice. The AGERP lecture series is a pro bono initiative led by Dr. Partha Mishra and Professor Sarat Das. Initiated in 2020, it is aimed at disseminating the coupled learnings from academia and industry on some of the key topics in geotechnical engineering. The International Workshop on Unsaturated Soils was hosted in 2022 during the third edition of the AGERP lecture series. The following lecture on inadequacy of the conventional pore water concept in geotechnical and geoenvironmental engineering was delivered by Professor Ning Lu at this workshop. Professor Ning Lu has been working on fundamental concepts of effective stress and soil suction in the past 2 decades and made some breakthroughs. He has unified soils effective stress under both saturated and unsaturated conditions, moving beyond the classical Tertsigis and Bishop's effective stress representations. For his seminal work on unification of effective stress, he received a SCE Norman Medal twice, first in 2007 for conceptualization of suction stress, and second in 2021 for formulation of a practical closed-form effective stress equation. He further defines the general thermodynamics-based pore water pressure in soil under both saturated and unsaturated conditions. In the past 2 decades, he has formulated a new paradigm for slope stability under variably saturated conditions, which has been bestowed by ASCE for its 2017 RB Peck Award. He has published 2 widely used textbooks, Unsaturated Soil Mechanics in 2004, and Hill Slope Hydrology and Stability in 2013.
What I'm going to talk about is actually one of the very important issues in geotechnical and geoenvironmental engineering, specifically about the pore pressure. We know that the pore pressure is so important for the entire discipline. And even today, we still have a lot of challenges that deal with them. And what I would like to talk is what are those challenges, particularly from practical perspective, as well as fundamental. And I'd like to also remind you the fundamental basic definition that have been used today for pore pressure. And based on that, and I will actually present you a new definition, very general definition about the pore pressure. And I will illustrate why those new definitions are very important in terms of geotechnical practice, particularly on soil property. Finally, I'd like to also share with you about the bright prospect for the upcoming years for us to continue to tackle this problem in a variety of geotechnical engineering problems. So what I like first is to look at what is the pore pressure, particularly at the scale that where we are concerned at the microscopic particle scale. What you see here is a sandy soil, fine sand, and under partially saturated conditions. So we have water, we have air, and we have, of course, soil particles. At that scale, the scale is very important. How we define the pore pressure. So the large pore, basically, if you look at the pore pressure, anything greater than micrometer, the pressure actually could be tensile under partial saturated condition. At the current, what we understand is the pore pressure could be as low as 0.1 megapascal. Below that, it's going to have a cavitation, mostly. And also this pressure that we talk about is directly measurable from the conventional sensors. But if we look at a little bit more close to the particle surface, what I'm talking about is the scale that less than 0.1 micrometer. Things are very different. And there, the pressure actually could be very high and compressive. And it really does not matter whether it's saturated or unsaturated. The pressure is in the region where actually is tremendous compressive. And most difficult now is it's not easy to be directly measured. Now, I'd like to give you some perspective about what I'm throwing out of the magnitude here. On the compressive side, I'm claiming that the pressure actually could be very high, 1.6 gigapascal. So let's get an idea about how big it is. If you look at here, I illustrate it as a marijuana change under the below the ocean. We know that deepest the one that the challenge that vehicle can go is 11,000, around 11,000 meters. So the pressure edges could be very tremendous if you imagine that you will be there. And to put a scale of the Mount Everest, the Himalaya, and we have 8,884 meters. And even though that is below the ocean, so the pressure is very high. How big it is. So let's do some very simple calculation using hydraulics. The pressure of water pressure that we all define, we all use it. It's basically below the water under hydrostatic condition is basically the unit weight times the depth. In this case, unit weight of water times the depth, which is around 11,000 meters. What we get is about 108 megapascal. So 108 megapascal is about 1,081 times higher than our atmospheric pressure. So standard atmospheric pressure at the sea level is 101.3 kilopascal. So basically that pressure underneath the marijuana change here is 0.108 gigapascal. But here we talk about in soil, near the particle surface, the pressure actually could be much higher than that. And why the pressure near the particle surface is so high? And that's because fundamentally because of soil electrical potential. The soil is a compound of silicon oxygen hydroxide, and they create an electric magnetic field. And those electric magnetic field will tremendously affect anything nearby, particularly like water. Water is a polar material. And so that will induce the pressure. The pressure could be, as I claimed here, 1.6 megapascal, and which is roughly about 15 times the pressure on the bottom of marijuana change. So what I'm saying is that if you go out to, in your garden and you take the soil with the moisture, the pressure actually near the particle surface, it doesn't matter whether it's saturated or unsaturated, it doesn't matter whether it's silty, sandy, or clay soil. The pressure could be as high as 15 times compressive than the bottom of the marijuana change. So we wonder, why is that? And I'm going to explain to you today. And why bother? What are the practical challenges? So I'll give you a group of the practical challenges that we are all facing today. The first is we talk about soil, we will deal with the fundamental physical property. And evidence in the last century has shown that the density of water in soil could be very high, much higher than the Unitary. How high it is? The evidence that show that it could be as high as 1.8 grams per each cc. So which means 1.8 times of the free water, as heavy as that. And that actually causes a lot of important issues that how we calculate, for example, how we calculate the volume of water, as an example. And the other thing is about the soil water cavitation. So we know that the water, like many of other material, in our near Earth environment, exists three phases: the solid, liquid, and the vapor. And it's going to change it because water actually is the only material that can change so freely near our Earth environment. It can change it to the ice, it can melt, become liquid, it can vaporize, become vapor. So it is very important to know that the transition actually, one of the important is called cavitation, which means a change from liquid to vapor. And the reverse process is called condensation. We can also run vapor to liquid. So why the soil cavitate, the water cavitate, is because we know that the liquid state, the water, when you have a major potential less than a certain value. The other important is about freezing. Freezing, we know that the water below certain temperature and pressure, it's going to go into the solid state. And however, when we have the water go into soil, it's being observed experimentally that actually water does not freeze at the 0 degrees Celsius. And it actually can be depressed as low as minus 22 degrees. So why is that? Actually has all consequences. For example, in permafrost, in thawing and freezing zone, 1/3 of our land of planet Earth is actually subject to change in water phase between thawing and freezing. The second category I put it as a general is the geotechnical engineering. So we know that some of the outstanding problem, expensive soil, for example. We all know that expensive soil, when you give it water, which basically is a 2-to-1 smectic family, and the volume actually can change from dry state to wet state 300%, not a few times in volume if you don't give any constraint. We also know that it's widely spread that when the clay material is subject to drying, it's going to have a crack. It's going to create what we call desiccation. So the behavior like that, sometimes people, we create different theory. But why is that? That has a lot to do with what I'm talking about at the water pressure. And the other very important is about the loess. Loess is a yielding cause soils actually widely spread around the world. Sometimes we call it collapsed soil because upon the wetting, the volume actually can reduce dramatically. So those are the issues that are actually very important and relevant. In fact, it's about the pore pressure. And we have not been able to actually tackle the issue from the true pressure point of view. And what we have done is from the conventional point of view to define the pore pressure. The other category I put, just give example, is the so-called geoenvironmental, which relate to the environmental problems. And we're concerned about how the water is going to move in soils, in rocks, particularly in clay soils. Because in clay soil, we have, in addition to conventional flow, we also had a larger surface area, which causes chemical absorption, physical absorption, and the water not only move in the larger pores under the Darcy's law, but also move around the soil particle surface, sometimes we call film flow. Biological activity in soils. We know that any kind of bacteria and germs that living beings, we need to have a certain kind of pressure and temperature. The pressure that we use conventional in the larger pore may not be necessarily relevant to actually the real condition where the bacteria scale, that is the living being and down to the bacteria scale, they're very concerned about. And that pressure is what we'll talk about. It could be up to a gigapascal. Energy transfer in soil, another example, how the water energy is going to transfer between atmospheric and subsurface among the soils, evaporation, transpiration, and water balance. So all those are actually very much related to the pressure in soils. If we look at it more fundamentally, the fundamental, what we talk about, the challenge here is we want to describe the state we have in terms of engineering practice, in terms of natural environment. Most commonly, we use temperature, pressure. In the case of unsaturated, conventional thinking is a suction, and I'm going to show you that's not always true. Even under unsaturated condition, it could be compressive. And stress, that we're concerned about total stress, the stress in the soil skeleton, we call the effective stress. How can assess the effective stress also relate to the pore pressure and the water content. In many cases, the soil's state is determined by water content. So I'm listing 3 basic fundamental issues that actually relate that we still, to great extent, we struggle with. The pressure and pore water pressure, or water pressure. So what we talk about is water pressure is pore pressure. Positive for saturated and negative for unsaturated, that's a conventional right now we're thinking about. And I will show you today that thinking is actually not general. I wouldn't say wrong, but it's not general. Stress, matrix suction, we talk about that. This is one of the things that has been widely used as a stress state variable for matrix suction. And how to define matrix suction, and how to measure in terms of from the practical perspective. Suction stress, effective stress, and how we can define, because effective stress is the one we call effective stress. Basically, it's effective to describe both deformation and strength. So water content, again, water content, the water content, we conventionally use a volumetric water content, or we can use a grammatical water content. Which one's better? Or maybe you have to use something else. So those are the fundamental challenges. So let me now go back to what we are doing today to make it clear how we define the conventional pore pressure. From there, we can look at what will be the better way to do that. So what I show you here is a very typical, let's say, a soil. Soil is a system that with the solid and liquid, and in some cases could be have air. In the case of saturated, what we traditionally, conventionally measure is use the so-called piezometer. So we can put the piezometer insert into soil under saturated condition. Likely the pressure here, you're going to see that the head is going to be higher than your atmospheric or ambient condition. So we call piezometer. And here I'm talking about under hydrostatic, no kinetic energy, the movement, just the hydrostatic condition. So the piezometer generally reading is what we call a compressive, which means bigger than the atmospheric pressure. Now, if the soil is under partially saturated condition, very often if you measure that one, it's going to have a deficit we call tensiometer. So which means it's going to be lower than your reference atmospheric. So those are all measurable. Those are all measurable at the scale greater than, I would say, the micrometer, even tens, 100 micrometers. So we can measure that one. So that's how we use it, how we define the pressure. But in the case also, much more general, if we have a salinity, if we have a solid in soil, we can also measure the osmotic pressure if we put the membrane there, semi-membrane, which means allow the water to freely move, however, to impede the salt because the size of the semi-membrane. In that case, you can also measure the osmotic pressure because the salt in soil not only migrate from high concentration to low concentration, but also it's going to drag the water from the high concentration to low concentration. So conventional pore pressure is the water pressure in larger pores, which means traditionally greater than micrometer or so. However, what happened in soil, if we look at it carefully and we zoom down to the nanometer, to the water molecular scale, and we do that, what we see there is the particle surface. Near the particle surface, the water actually have two mechanisms interact with water. The first mechanism is the absorptive one, which is very much due to the influence of electric magnetic wave by the soil particle, because the water is a polar material, it will be polarized. And further away from that is what we call the capillary water. Under saturated condition, it could be no air, but under unsaturated condition, it could be some air, and then you can have some air-water interface, and that is dictated by the pore size. If you look at the qualitatively, the pressure, in fact, is if we use the air pressure as a reference, atmospheric, right beneath the air-water interface, it actually is what we call negative water pressure. In other words, it has deficit. And that is because the tendency of water, tendency of soil to drag water, it causes this concave interface. And then we will see that the actual pressure remain negative for considerable amount if we go close to the particle surface. Until somewhere when the water actually gradually transition to absorptive water. And that you see that the pressure is going to increase tremendously, and it's going to increase in the gigapascal scale. And by now we can quantify that one. And we're very confident for all soils, whether it's sandy, silty, clay soil, the water near the particle surface in the absorptive water, it goes shoot up to the compressive. Doesn't matter whether it's saturated condition. Now, correspondingly, because the pressure is so high, it goes to the gigapascal, you're going to see the water density near the particle surface. I'm talking about 100 nanometer, 1,000 nanometer. Within that range, the water density actually is going to be shoot up way bigger than Unitary. In other words, it can go as high as 1.8. So far, the experiment evidence indicates so. What are the difficulties? So if you look at how we do that conventionally, again, I use this fine sand as an example. we can measure the air pressure with no problem at the moment, the technology. We can also measure the capillary pressure. I'm talking about the pore pressure. They use a conventional one. And however, if you look at near the particle surface, the pressure actually changes quite a bit. So in particular, the pressure here near the particle surface is a distance I call X. I'm talking about hundreds or less than 100 nanometer, that kind of range. But it's important, you can say why, but it's so small. For sandy soil, maybe that's not important because because the surface area is small. But for clay soil, it could be very important. So the question is, we have a pore pressure, which we call a capillary pressure. What about absorptive water pressure? How big it is? And also, by now, we all define matrix suction as the differences between the air pressure and water pressure, which everybody here, I think, probably know that. I would say the popular theory for unsaturated soil is to consider matrix suction as the differences between air pressure and water pressure. Is it true? Is it good as the fundamental variable if we define that way to describe phenomena in unsaturated soil? Well, let's look at the water phase diagram. So any matter, as I said, it could be in 3 states, depending on the pressure and temperature. Water is no exemption. And typically they are in the 3 states. Somewhere here is a liquid, somewhere here is a vapor, and somewhere here is a solid. Now, what makes this phase diagram is the pressure and temperature. Temperature, we know that you average it, you measure that on the molecular scale. Pressure, again, has to follow the molecular scale because we talk about water molecule. If the pressure between 2 water molecules reaches certain kind of stress, they're going to have a phase change. So that is dictated by the molecular scale of water. It's not dictated by what we measure conventionally in the much larger, greater than micrometer, millimeter scale. That's the nature of the product of the water. So basically saying that if we use a large pore pressure, we cannot describe the phase. We cannot describe how much water in the ice phase, how much water in the liquid phase. What dictated one is the true pressure we call intermolecular pressure. So let me ask a few important questions that I think a lot of people doing unsaturated soil will all deal with. Is the matrix suction equal to negative pore pressure? So negative pore pressure, the short answer is only for capillary water pressure. It does not reflect the absorptive water pressure. So you may wonder, what is absorptive water pressure? I'm going to talk about that. Why does water pressure vary with distance? In other words, the distance to the particle surface. What makes that? I already mentioned that. It's because of tremendous strong electrical magnetic field surrounding the soil particle. And those could be further divided, and I will do so into a few different mechanisms, such as hydration and the van der Waals force, so on and so forth. But answer to that one is because we have absorption in addition to the capillarity. And that is why it very much depends on the distance to the particle surface. Can we use the matrix suction for water phase change? The answer is no, because matrix suction by our definition is a larger pore air and water. But very basic physics is that what dictates water is the ice and or solid or liquid or vapor phase. It's not the pressure that we conventionally talk about. So it's what we call the local pore pressure. So the question is how we determine the local pore pressure. Can we do that? And I'm going to share you today that in the last decade or so, we have a series of breakthroughs that allow us actually, to the degree that we can tackle that problem. We can have a very clear way to define that and to quantify that. So let's come back to the phase diagram water a little bit more carefully. In fact, it is not that simply only 3 phases. If you look at the pressure and the temperature, temperature here in Kelvin, and the pressure here, I use a megapascal. Here is the liquid part, here's the ice part, here's the vapor part. And in this area, that sometimes we call triple point, below the triple point, somewhere here in this region, the water is so-called in the metastable state, which means that it can be in the liquid, it could be in vapor, It really depends on some other factor, that purity and so on and so forth. So that's called a metastable. That makes the things actually a little bit more complicated. And that is actually explain one of the reasons, for example, people put a saturated ceramic stone. In a saturated community, people know that. You can saturate the ceramic stone, but however, it's subject to cavitation. Why is that? Because when you apply the negative pressure, lower than FMS factor, you are in this so-called metastable region. Metastable means that they could be either way. So, but the pressure in soil that we can actually conceptually now can be actually divided into two parts. One is due to the capillarity, which we can use a convention to measure. The other one is due to absorptive pressure. So this absorptive pressure is the one that my focus today, to share with you some of the breakthrough that we get to the degree actually we can quantify experimentally, theoretically, very well for any soil. Now, let's look at what concerns us in the near Earth environment for all of us, geotechnical, geoenvironmental area, is that this is the area that actually the temperature is subject to this change, as well as the pressure. So we see that from here that we actually have to concern about the ice, we have to concern about liquid, we also have to concern about metastable, that eventually can go to the vapor phase or so on and so forth. I'm going to use an example to illustrate that this local pore pressure concept due to the absorption. So I do some thought experiment, say, okay, we can have the martini cup to have a punch to drink. But however, the scale is very small. The cup is a micrometer scale. So scale is everything here, because when you go to the micro, sub-micro scale, the molecular force start to be in action. It start to take over rather than the, compared to the gravity and others. So let's define what is water pressure. So water pressure is an average of interwater molecular forces per unit area. So that's how we define. So intermolecular. So we have to define the water pressure down to the intermolecular. Why we want to define that one is because what dictates the phase relation of whether it's a solid, liquid, or vapor. It's not what we conventionally measure. Rather, it is an intermolecular scale. So it's a component. The water pressure is a component of water potential. Sometimes we call water potential, or sometimes we call matrix potential. It's basically the energy that's stored, mechanical energy stored in a unit of volume of water. Capillary pressure, let's also make clear the definition of capillary pressure that we have been using equivalent to matrix suction, which is not. So capillary pressure basically is the pressure difference between water and the air. So that's how we use it, because that can be measured. Now, if I were concerned about the pressure near this 1 micrometer of a soil cup, here, let's say a certain distance I call X. What is the exactly intermolecular pressure? The intermolecular pressure actually could be divided into many parts that can cause that one. We can have the osmotic part, because you change the salt. We can also have the osmotic part is because the salinity that we put at that one. We can have so-called electrical double layer, because the particle surface, most clay particle surface has a negative charge oriented toward the particle surface. Then we form the electrical double layer. When the water molecule go there, they're going to change the pressure locally. But that is due to this electromagnetic field. We can have so-called van der Waals. The van der Waals is another type which is clearly understood in physics. That again, it's due to this electromagnetic imbalance there. And we can also call it hydration. Hydration is due to the oxygen, hydroxide, and those kind of in soil compound. They can also attract water, orientate water. So all these are electrical magnetic underlined here. It's electrical magnetic in nature. However, they convert to water pressure near the point where we are concerned about. And further, we can have the pressure difference between air and water, which is called a capillary water. The difference between that one. And of course, finally, everybody know that if you're under the gravitational field, and you can also change the pore pressure. Just like if you have a swimming pool, as you go to below the water surface, the pressure is going to increase linearly, right? linearly roughly because we consider about gravity. Gravity is a constant. Strictly speaking, it's not exactly the constant depending on the location, but if you consider one, so it's a linear. So that's the final term here. So actually, each of them is under different potential. But all this, capillary as well as gravitation, we all know that. The question here is how this electrical magnetic in nature that affected the pressure near the particle surface. That is something that has been actually recognized for many, many years, but eventually has not been able to unify that. And we do so in the last decade or so. So let me present by now that the very general definition of the pore pressure, which including the two mechanisms I'm talking about, capillary and absorption. So the two very different distinct physical mechanisms actually can change the water pressure in soil. One is the capillary, which we all know by now very well. In fact, most of the theory for unsaturated soil mechanics is built on this concept of capillary. You name the Bischoff, Finlands, they always use the pressure difference in the air and the water. And there's another part that we have been missing by and large, which is the absorption. And that is the one I would show you today. The last decades, a few breakthrough allow us actually now to quantitatively describe that. So pressure, again, I want to make it clear the pressure that we talk about is, in fact, the physical meaning of the pressure is energy per unit of water volume. Well, you can work out like energy per unit of volume of water, right? So you can Joule become Newton times meter and divide by that. And then eventually you can go to Pascal. So we call pressure. When we say pressure, Pascal, we usually just think about it's mechanical. In fact, it actually refers to energy per unit of water volume that you have. The capillary pressure that we have been talking about only exists in soil under unsaturated condition. So that is one of the things we all conventionally think about. And then we use this definition. This is macroscopic. Again, this definition does not allow us to describe whether water is in solid, liquid, or vapor state. It only describes certain state that we talk about. There is a capillarity, existing capillarity, and the severity, importance of the capillarity. The big part of that is the absorption-induced pressure. We all know that the soil, sandy soil, different than clay soil in behavior, whether it's saturated and unsaturated. In fact, the major difference is because it's absorptive pressure. Because absorptive pressure exists whether under the saturated condition or unsaturated condition, they all exist. So that is something very important to understand that. The absorptive pressure, how to quantify that one? Because we just talked about it, actually originated from a series of electromagnetic field. Specifically, it comes from the osmosis, it comes from the electrical double layer, it comes from the van der Waals, and it comes from the so-called hydration. So all this because it's electrical magnetic field, and it will polarize the water. The polarized water is going to induce pressure. So we can actually collectively call this called soil sorptive potential. So the key here is what is the relation between these two? So we define the water pressure in soil as a function of water content and distance to particle surface. And it can be divided into two parts. The capillary part, which has nothing to do with the distance, it's in the large water, we call capillary menisci. But however, the absorptive part not only depend on the water content, but also depend on the distance you're talking about here. And that could be linked to the soil sorptive potential, which has a different mechanism. So if we be able to quantify that, theorize that, quantify that one experimentally, we actually can answer this question. If you know the soil, and you will know how the capillary pressure as well as absorptive pressure. So one of the breakthroughs that I would like to share with you is how we define the matrix potential in a much general way, not just the capillary, but also the absorption. So how we define that one, you can look at the soil elementary volume here. That to be representative, we need to do both the solid, liquid, and the vapor. And that is something that when we define matrix suction, we have to have the three elements in there. So that is something that by definition. However, if you look at when we defined in Laplace-Young equation. The Laplace-Young equation that we have typically to describe unsaturated soil, to describe particularly capillary pressure, it actually involves the air phase and the liquid phase. Further, if we look at the pressure that I'm talking about, local pressure, now intermolecular pressure, which determine the water phase, as well as I will show you today, many of the soil property, in fact, it is at a much smaller scale. It's an intermolecular scale. So we have this kind of, the challenge that because of the inherent of the discipline, and by definition, some of them at the much larger scale, some of the small scale. The key is, what is the relation among these two of them? We can establish it by what we call the local thermodynamic equilibrium. So which means if we look at a small particle and water, when they reach the energy equilibrium, every point, the total head, we call it the total potential, has to be, the water potential has to be same, although it could be in a very different form. Near the particle surface, you can have electromagnetic, much more polarized, and then it induce higher pore pressure. Away from that one, you can reduce pressure. You can even go to negative pressure. However, the total potential is the same. It's just like a gravity, that we have a gravitational elevation. We have an elevation head and the pressure head that can change it, but they have the same total head. Here, the concept in the local sense, it's the same. So if we apply the energy equilibrium, we actually can find that the metric potential here will lead to the energy everywhere is the same. The metric potential has the two components, the capillary components and the absorptive components. Quite straightforward. If you look at the pressure under the same total potential or metric potential, whether it's away from particle or whether it's close to particle, it's the same constant. And you actually can divide into two parts. One is due to the capillary part. The other one is due to absorption part. So that is maintained, but if you add that two together, it's going to get that constant. So here we have this relation between the matrix suction, which I have two components now, the capillary components and absorptive components. And we can have, again, the same, we can define the water pressure. The water pressure not only depends on how much water you have in soil, but also depends on where you are talking about, close to the particle surface. Again, this can be divided into two parts. You can have the capillary and absorption part. How to determine that one? That is one very important, and I call it breakthrough number 3, is now we can actually precisely, accurately measure that. So how to measure that one? We don't directly measure pore pressure. We measure the total potential, or we call the soil water isotherm. So here's a device called the vapor absorption analyzer. That we control the humidity, we measure the relative equilibrium water content in terms of gravitational, gravimetric water content. And here is an example of the mixture of bentonite and kaolinite. You will see that the wetting, drying, there's some hysteresis, depending on what kind of soil. The more expensive soil you have here, the more hysteresis. But basically, we can measure the equilibrium condition. We can determine total pressure. And we can use the relation I just showed you to quantify the pore pressure. So once we have the experiment data of isotherm, we can unambiguously divide into two isotherms. One is due to the absorptive isotherm. The other one is due to capillary isotherm. And the capillary isotherm actually is the one that we can use to get a particle size, a pore size distribution. And the absorptive isotherm is the one that which can actually determine the pore pressure. So depending on the initial soil water content. So we can first determine the soil sorptive potential from the total potential. And then depending on what kind of initial water content you have, you're going to have a different distribution, ambiguously calculated. And this is an example we use Eli material, and depending on what kind of water content. And for expensive soil, we can actually even quantify the swelling pressure inside the crystalline and how much it is, and depend on how much water content you have. So we can answer that question. So let me right now, by now I would like to share with you some of the importance for the soil property we use for our discipline. The first one I'd like to show is the soil water density. And we have been using the soil water density to define the head, to define many of the quantity, to calculate the volume. In fact, it is not a constant. And here, what I give you is an example, is some kind of expensive clay. And you can see that the water density actually can be much higher than 1 unit. And if you measure the soil water retention, the soil water retention curve actually can be divided into the capillary water retention curve and absorptive water retention curve. In this case, the absorptive water could be up to greater than 0.1. So the water density, it can be tremendous. Another example is elastic modular. We know that when the soil, particularly clay soil, you have a lot of water and it's going to become softer. When you dry it, becomes very hard. And here again, you can see the soil water retention. I give example, this is an expensive soil. The absorptive part and the capillary part. And then correspondingly, you can see that the modular change, this total modular, and there's a hardening due to capillary and it's hardening due to absorption, depending on water content is in. So it's very important that we can actually now using this concept to quantify the role of each of them in terms of the property. I'll give you another example, small stream shear modular, which dictated the wave velocity in soils and rocks. Again, we can give an example here is a silty soil. And the small part is the absorption, and then the larger part is the capillary. And together is the soil retention. And you can see, however, if you look at the small stream modular, this is the part controlled by absorption, and this is the part controlled by the capillary. Another example is about the freezing. The freezing, as we know that the water in soil is not just freeze at 0 degree. Great portion of the water, in fact, it's going to gradually freeze until somewhere go to the minus 22 degree, where the actual water start to change the structure completely into the solid chain. Somewhere between that, I see that this is a depression of the plant temperature. Again, that you can use the concept of soil water retention to divide into the absorption and the capillary. And it directly uses this information to predict precisely what will be the soil freezing curve once we decode them. Thermal conductivity, we know that we use energy foundation. One of the important properties is thermal conductivity. And here I illustrate the two soils. The bentonite is Denver, claystone is Eli, and then compared to the sand. Sandy soil actually is just going very high in terms of thermal conductivity from dry to wet, versus the clay soil, it's actually changing gradually. But both of them actually you can divide it into the capillary water and absorptive water, same thing for here. And you can use that ability theory to actually quantify, to predict that thermal conductivity. Another example I would like to use is the effective stress. So we know the effective stress is a part of the stress that's sustained by the soil skeleton. So far in unsaturated community, we have quite a few of the theory. One of them is early by Bischoff, and then the Fedlin and Morgenstern, and by myself and my associate. And if you look at that at a fundamental level, the Bischoff effective stress only consider about capillary. Why? Because it consider about capillary pressure times a dimensionless quantity, which basically is upscale. So this is still satisfy the stress criterion. However, it is only about capillary. If you look at two independent stress variables, both of them are incomplete in terms of stress variable because they only use a part of that. This is the capillary pressure, not the stress. You need to be upscale to make that one. You also miss the absorption that induced. So it's only part of capillary. But if you look at the suction stress, which I have formulated in the last 2 decades, that including the both suction stress, both capillary stress and absorption stress, and it's a stress quantity. Now we actually can pin back to fundamentally why there is capillary stress, why there's absorptive stress, and how we can quantify for that. And I show you that the latest that we can unify the effective stress under both saturated and unsaturated, any kind of soil, is the suction stress representation, same form with the effective stress, like Tazaki, except that the suction stress depend on your soil. It becomes a constitutive relation. Here I show suction stress as water content. We can have unambiguous divide for any soil, the absorptive part and the capillary part. And you add them together, it's going to be the effective stress in soil. And with a few parameters that actually has all very clear physical meaning. So I'd like to just provide by now a little bit about my perspective for future. I think it's very exciting for all of us to continue actually to expand and to even to use that concept for geotechnical and geoenvironmental engineering. First, I look at that is in the soil property. As we know that now we just start to begin to realize that soil water density, it's not a unit. Soil water density in clay soil could be as high as 1.7, 1.8, which means that actually the way we calculate the soil phase diagram, it is incorrect, it's wrong in clay soil. And recently I have done that, we find that, for example, for expensive soil, the error actually due to the phase relation, it could be way over 30–40% in terms of volume. So it's very important to look at, again, what will be the soil water density, how we measure that. It becomes so far, and there are some methods, but still very challenging. So that opened a new windows for us to do that. And fundamentally, the water density also can be related to the specific surface area. Water cavitation, we deal with water in three phases. In subsurface, it could be evaporation, condensation. In the cold environment, it could be freeze, it could be thawing. And all this is very important is to understand how the water pressure can be defined, the true pressure, and the freezing behavior. And the other area I'm talking about is a geotechnical problem, and we can solve expensive soil. Expensive soil, by now, it's all using so-called swelling pressure, which is basically is total stress, rather than look at fundamentally how the pore water pressure changes at the intermolecular scale, inside the lamina, outside the lamina, how they distribute the energy, and how much energy actually is going to contribute to the swelling behavior. So this opens another new door. Mark cracking, again, come back. Mark cracking is a widely problem. If you have a clay liner material, one of the problems that for the integrity of the performance is creating crack. And why is creating crack? Fundamentally, we don't change the total stress. What we change is the suction stress. It's an interparticle stress due to absorption, more than due to capillary for clay material. So it's very important to understand from the mark cracking loess. Again, it's collapsing soil, we call. In fact, loess does not necessarily collapse upon wetting. The volume actually could be swelled constitutively. The collapsing phenomenon, by and large, is because of the boundary value problem, because of the overburden we have to cause the failure of the material and post-failure behavior. But fundamentally, we can look at it from the point of view of how the pore pressure is going to contribute. And I'll show you some of the geoenvironmental application here. We can have the understand how the water and the transport in clay material, including the chemical absorption. We know that the different kind of species that actually absorb in soil differently. But fundamentally, it's the same like how the water is going to absorb in soils, because the interaction between the soil and the non-polar material. The water flow in soil, particularly in clay soil, is no longer just governed by the capillary water we call Darcy's flow or Poiseuille's flow. It actually can be controlled by absorptive water. So that opened a new channel for future for us to understand how the water movement in soils. Biological activity, temperature, pressure is dictated all those biological activity. Are we using the right temperature and we're using the right pressure to understand the biological process? And finally, the energy transfer in soil and how the atmospheric interact with the subsurface, which is one of actually right now the research frontier for many disciplines. So by now, let me make some conclusion of what I talked about today. The conventional pore pressure that represent actually is the bulk water, large or sometimes we call capillary water. It actually ignores the local pore pressure due to absorption, and it's inadequate for geotechnical geoenvironmental engineering application. Absorptive induced pore pressure is actually localized but very high in compressive mode, It could be up to 1.6 gigapascal under both saturated and unsaturated conditions. And the way to generalize that is how we define the pore pressure, which has two components now, the capillary components and exotic components. We can experimentally quantify for any kind of soil to determine that under any kind of water contact. Finally, I think the absorptive induced pore pressure, as I just showed you, has a propounding impact on soil property and many practical geotechnical problems. Thank you. Thank you all for your attention. Loading type, when you say loading, you mean the mechanical loading or also the hydrological loading? If you only talk about mechanical loading, the mechanical loading, it actually can change it. If the loading is such a degree, they actually can change it, for example, the fabric. And then actually you can change the suction stress because fundamentally suction stress is interparticle stress. It actually exists both at the contact as well as near the contact. So if your soil under the mechanical loading to that degree, then it actually can modify the contact area, resulting different suction stress. The second, environmental, of course, the environmental loading is one of the leading factor that changes the suction stress. And that is why in the formulation that I have so far, the water content, or you can use a degree of saturation, or you can use matrix suction or matrix potential as a variable. So it is environmentally important. That is a question still remain to be researched. But if intuitively, I think that the mechanical loading, traditionally that we're all concerned about the mechanical loading because a few thousand, up to a few thousand kPa is the one that actually caused the change of the structure, both deformation and the strength. However, if you look at the environmental factor, the water content change or the matrix potential change, particularly for clayey soil, the induced stress, I call suction stress, which is internal, it actually could be up to 1,000 kPa. In fact, this is the one that under the cyclical loading, and we see a lot of structure infrastructure failure after this type. So I think it's equivalent importance. So by now, the van der Waals is one called AGERP potential is one of the four, and in fact, it is not necessarily the most important for clay soil. It is important for silty soil. Why so is it because clay fundamentally different. There's another mechanism, as I already put it on, is the hydration. When we have an expensive clay, the hydration, interlayer hydration, it actually far exceed in terms of energy. If you look at some of the paper I put it there, if you compare to the film AGERP potential. So, but the four components I put together called soil sorptive potential, it's not new. It's been there for a century. However, I'm the first one to put all four of them together. And if you look at different disciplines, in some ceramic material science, the AGERP potential is very important. But if you look at some other discipline, the van der Waals could be very important. But put all four together because they all are electrical magnetic in nature. It's how much they induce water pressure. So that is the one that I put together. So collectively, and I would say that depend on the certain stand. If you talk about kaolin-like material, for example, the film water, it's very important, the potential. But the hydration may not be that necessarily important, but expensive soil, it could be very important. So it really depends on what kind of soil you have, all these four components. Yeah, but I would suggest you, there are a few of the papers that I published. In fact, I put for the first time, all of them in terms of order magnitude, where they're going to overlap. And what kind of soil that actually you're likely to have, and that kind of each of those components. Well, yeah, I think that question, the way I look at it is even though the pressure could be tremendous locally, but they are self-balanced. So which means they are not going to crush your soil grain at all, because the attractive force due to electromagnetic is counterbalance. So it's not because pressure is tremendous then you're going to crush the material. No, it's not, because it's a self-balance. It's like an action reaction.
No, thank you.
So that's why when you go to the garden now, if you pick a soil, it's a sand, still loose sand. But if you look at it, you zoom into a 3 water molecule, the pressure is a gigapascal. But that pressure does not crush your sand grain, because it's a, action reaction is just self-balanced. It's a self-balanced by a force well-known, sometimes called Bohn's repulsion.
I would like to ask a question, Professor Lu. So very, very nice presentation, very impressive. I was wondering whether you could think of a scenario where we can lose or change the adsorptive forces in the soil due to geochemical processes, for example, when the chemistry is changing of the pore water.
I think that there are many of the examples that could be. For example, I can immediately think about it. We sometimes call it sensitive clay, right? So you just mechanically disturbance, because geologically they form some kind of metastable due to the physical chemical absorptive force particular. But when we do a mechanical disturbance, they're going to change the property tremendously. They can become liquefied. And a lot of to do with this disturbance of local in mechanical. But by the same token, that they are similar, that chemically you can change it. For example, some of the soil that originally like water, but if you do some kind of treating, they can dislike the water. When they dislike the water, they change the pressure locally very differently, and correspondingly the property is going to change. So the answer is, I think that actually I feel that many of the questions can be tackled by the concept here.
Yeah, quickly could be one of these. You mentioned it already with the liquefaction, when it was deposited under saltwater environment and the salt was washed out over time.
Right.
Yeah, it's an interesting problem, especially when you think about timescales. And we are working together with some colleagues from minerals processing, where we look in similar issues for tailings. Yeah.
So the tailing material, the other things that some of my colleagues start to work is here I talk about the absorption of water on soil particle. In fact, in principle, it's the same like other species. You have some other chemical compounds that also absorb particle surface, and as a result, they're going to change your mechanical property. But it's a similar concept. It's basically electromagnetic field due to the solid part, and then you have a polar material. In the case of a polar material of water, but in other cases you can have other polar material of other chemical species.
Yeah, and we try to look into this as well from an electromagnetic point of view to measure volumetrically the components, the phases of individual. It's a bit tricky. Water phases. There is then a bit of an overlap. What you look at, is it a solid phase or the water phase? But yeah, there are approaches to try to quantify these phases. Yeah.
Well, I'd be glad to discuss it further if in the future, if you have some problem questions, then we can actually do some collaborative research and try to better understand.
Yeah,
I'd be glad to do that.
Really fantastic.